So we've got here this circuit on the right that has two resistors in parallel. And we want to know what must be true about the potential difference across these two resistors. So remember last class we talked about the fact that when you've got two resistors in series, you have to, the potential drops across each one of them, right, such that the potential difference of two resistors in series adds to whatever the potential difference of the overall battery is. Okay, so how about in parallel? How would you answer this question? What must be true about the potential difference delta V across these resistors? Do they add like they do in series? No, right? So the potential difference is the same, right, across these two resistors. So it's the same. And not only is it the same, it's the same as the EMF of the battery, right? So the drop in potential across resistor 1 is equal to the drop in potential across resistor 2 is equal to E, right? So if this was a 9-volt battery, if this battery was 9 volts, you know that this wire all the way along here, this is an equipotential, right? So the potential all the way along this line would be 9 volts. Right? Everything along this line here would be 0 volts. Right? And so here, between here and here, would be a change in potential of 9 volts. Same thing with between here and here. Change in potential of 9 volts. Okay? So from a current point of view, so we've got current going through here, going through here, going through here. Right, let's call that I total. What happens to the current at this point A? It splits, right? It splits into, say, I1 and I2. And then it comes back together here. Right, so here this would be I total again. Right? And I mean, would the current through both of those branches necessarily be the same? No. What condition would have to apply for the current through those two branches to be the same? The resistors would have to be the same, right? So what must be true about the total current that flows through both resistors? The total current has to add, okay? So while the voltage adds in a series situation, the current adds in a parallel situation, okay? It's the exact opposite. So the total current would just be I1 plus I2, the current going through one branch plus the current going through the other branch. Okay, so how would we find an expression for the equivalent resistance if we wanted to replace these two resistors, if we wanted to replace them with a single resistor? So we want to have the same exact circuit, but instead of having R1 and R2, we just have one resistor that has what we call an equivalent resistance, to R1 and R2. Well, so what we would do is we would start with I total. So we would say I total equals I1 plus I2. Oops. Right? And we know from last lecture, Ohm's law, right? The change in potential equals the current times the resistance, right? And so we know that so if we wanted to say the change in potential of the equivalent, so equivalent over the equivalent resistance, right? That's going to equal R. So the whole voltage of the battery over the R equivalence, right? And then from there we can just sort of substitute things in. So VEQ over REQ equals the change in potential 1 over R1 plus the change in potential 2 over R2, right? And because these are the same, they cancel out, right? Because remember we're saying like the potential difference across the resistors is in parallel is always the same. So, so those cancel. So what you end up getting is the equivalent resistance is just this. Okay? So remember in series, the equivalent resistance, how did you find the equivalent resistance in series? You just added them together. Okay? So here it's like the reciprocal of the sum. Does anyone have any questions on that? Okay. So the am I getting it? I think in the interest of time, let me just give you the answers, and then you can try these on your own because I think they're actually probably easier than the questions you've already seen that are like this. So unless I don't know how much did you actually see of this in the review?